All right, good morning, everybody. Thank you for joining us for our free webinar today. I'm sure more people will be jumping in. If you have questions, go ahead and list them on the chat, and we will address these questions at the end of Jonathan's presentation. So today, I have Jonathan Madren presenting, and he holds a BS in chemistry from the University of North Carolina at Chapel Hill, and a master's in geology from the University of Houston. He spent over 7 years working at Anadarko Petroleum, focused on organic and inorganic geochemistry, along with drilling and well site operations. Jonathan has worked on solving problems for U.S. onshore, offshore, and international projects. He currently works as the technical manager for Chemostrat, doing interpretation and integration of geochemical data, new product development, and laboratory operations. So with that, this is Jonathan Madren, and I will share my screen and pull up this presentation.
All right. Closer. Hopefully everybody can hear me here. I sometimes mumble. Let's see. Okay. All right. So I'm going to spend a little time today talking about some of the organic and I'm known for doing some of the inorganic analysis, but I thought I'd sort of talk about some of the organic analysis that can be done and how it might be able to answer some production questions. I'm going to mainly focus on gas analysis because that's, in some respects, the simplest and the easiest to sort of talk about, certainly maybe in this format, but there's trying to cover the topic of organic geochemistry, even in 30-minute talk, is probably pretty tough. And even this one area of it will have a fair amount of, will be fairly superficial in some respects, but hopefully we'll point to some real world kind of questions or problems that people have and how you might be able to use some of these data to help you solve. So that's what it is. I think I'm going to be like a pizza, 30 minutes or less with the talking, and then the people are going to get a chance to ask questions. We have a fairly, at least under my understanding, we have a fairly broad cross-section of people here, people that are fairly new and people that have a tremendous amount of experience. So we'll try to speak to everybody at least a little bit. All right. So one of the things I want to start out with, and one of the things I think is pretty important to mention, is that what I mean, if I say by that, I mean drill horizontal. They're really still petroleum systems, and so a lot of the ideas or tools that we have to evaluate normal petroleum systems still apply here. Again, you need to have, when you start out with a source rock, it may also be a reservoir rock. Sometimes you may have interbedded source and reservoir rock. They're not always the same, although they may be physically very close together. You certainly need to have a seal rock to keep in the hydrocarbons, and we'll talk about that a fair amount. And you need obviously overburden to generate the thermal maturity that you'd like to expect. So when we're talking about gas, there's three major types of isotopes that exist in nature for carbon. There's a man-made one that's really sort of an asterisk, but in the case of carbon-14, it has a half-life of about 5,000 years. So from the geological perspective, we're really not going to be very interested in it. We're really going to focus in on stable carbon isotopes, which are 12 and 13. And something like 99% of all the carbon that you see is a carbon-12. There's a small amount that exists as carbon-13. That's around 1%. And so whenever we're trying to talk about or discuss this sort of concept of the relative amount of carbon-13 to carbon-12, we usually use an equation to normalize it, which is kind of shown here, where you've got the carbon-13 and the carbon-12 of what you're measuring against the standard. Generally, it's PD belemite, but it could be some other standard depending on what you're interested in. Times 1,000, and that's just to try to get a set of numbers that are easier for people to understand. And generally, and perhaps that sometimes confuses people, is that most of the things we observe in nature, certainly for the hydrocarbons, are isotopically more negative, meaning that they're as you become more isotopically negative, you're depleted in carbon-13, and so sometimes that's a little bit tricky for people to see, but that's kind of the way it is, and it's because the standard they used, the P bell light, they used a 0. That was a decision made many years ago. All right. So another important point to start out with, make sure people understand, is this concept of thermal maturity. Usually it's represented by vitrinite reflectance. So what we have, vitrinite reflectance, you'll have anything from near the surface, starts at 0.2 or so, something on that order. And in that shallower interval, or the lower maturity interval, you'll have microorganisms that exist that can generate hydrocarbons, mainly methane. And they can either be the result of the breakdown of oil, or they can sometimes be the breakdown in very shallow intervals of some other things. But they're generally oil-based, sort of the breakdown. And there's a lot of talk that we could talk about for the microbial activity, but we'll sort of pass it to the side. Then you will kind of come down into the main, sort of the oil generation, main oil window, and you start talking about oil cracked to gas. And it's important to remember that most of the gas that you see is actually from oil that is cracked to gas, as opposed to being generated originally from kerogen. It certainly generates some, but a larger volume of the gas that's generated or that's seen is actually oil breaking down. Then you'll sort of go into around the 1,3 vitrinite reflectance, and you go into what people sometimes call wet gas. That's a little bit nebulous. It's where a lot of times you're talking about condensate, even to sometimes rich gas, so things that may have condensate that will condense out on the surface, and sometimes things that maybe not even have real condensate with them, may just be NGLs associated with them. And there's a pretty substantial monetary impact if you are going from something that is oil or mainly oil into something that's mainly gas. It's also useful to know that this is sort of a logarithmic scale, and so the difference between something that's 1.8 to 2 is a lot less than something that's from 1.5 to 7. Again, the scale of the vitrinite reflectance, a lot of people have some real challenges with that because it requires a human being looking down a scope and making a call that this is a piece of vitrinite that we're measuring. And there's been plenty of studies looking at how much variance you get when people sent things to different labs. They've gotten sometimes substantially different results. And a lot of the criticisms and challenges of vitrinite reflectance are very valid and true. However, it's the best that we have, and it's sort of the industry standard for what people sort of look at. There are other ways that people have to get some insight to thermal maturity, but vitrinite seems to be pretty the most robust. And again, certainly it's the one that has the biggest data set associated with it, I believe. Okay. So one of the things that we have here is with vitrinite reflectance is, or an observation that people made, was the idea that the vitrinite reflectance could be related to the stable carbon isotope ratio of methane. And again, this is sort of a general thought that you see here, but the idea is that, well, as I say, the general idea is that if you consider, remember the beginning part where we talked about that carbon-13 and carbon-12 were very similar to each other. Carbon-13 is just a little bit heavier than carbon-12. And if you think about bonds like a spring, they're not exactly that. They're more complicated, but they approximate a spring. It will take more energy to vibrate and break apart something that's heavier, physically heavier, than it will be something that's lighter. So the carbon-12 bonds tend to break down first, and the carbon-13 bonds will break down later. When you're talking about the microbial effect, it's pretty pronounced. But as you get more thermally stressed, you'll begin to break more and more of the carbon-13 bonds, and so you'll see more and more carbon. The methane will become more and more enriched with carbon-13 as you get more thermally stressed. All right. So now that we've got that background out of the way and sort of people understand maybe where we're coming from, let's talk about some examples of how you might actually use some of this stuff. So there's a unconventional shale that exists, and the people are looking to drill as an area they want to go in and develop. And so whenever you're going to go drill a well, you have to give your reservoir engineer or engineer, whoever you're going to give it to, some predictions as to what kind of well you'd expect to get. So whenever this was put into to be drilled, the idea was, okay, we're going to get between 4 to 5 million cubic feet a day of gas, and it should give us a yield of about 40 to 50 barrels per million. That's kind of what people are shooting for. And we have a couple of pretty closely spaced laterals. They're about 6,000-foot laterals. They're maybe about 1,000 feet apart, something on that order. And wells are drilled and fracked and turned on. And the first well, it makes much more gas, much more total volume than was expected. But the yield is a lot less. It's almost an order of magnitude less yield than what you'd anticipate coming into it. Okay, well then, it's right next to it. You drill and you get something that's like much less production, like 1 million cubic feet a day, but it's about that 50 barrel a million that you'd expect. So it's a very interesting question as to what's going on there and how much you solve that. So I'll just sort of illustrate what's happening here. So you have one horizontal that's sort of drilling. It dips down a little bit, right? So this is maybe the first well that was drilled. It kind of dips down a little bit into this sort of Marley zone that's between your target interval and your carbonate-rich interval. And so it dips down here, and then it kind of comes back up and goes into the target zone. Yeah, the second well you drilled, okay, now since it's close by, you've gotten better well control, better log control. You're able to drill it and steer it, and it stays totally within the target interval that you have there. So while we were drilling the well, we decided to take, let's say, for example, we decided to take mud gas samples. So you're able to collect gas samples as they come while the well is drilling, as they are coming off of the mud gas. So the gas, you can capture that. And the compositional amount of gas you see, so in other words, the ratio of C1 through C5, for example, that you see there, that ratio, say, of C1 to C5 can be skewed in the mud gas, depending on because you have different solubilities of C1 versus C5. So the composition, percent C1, C2, C3, C4, C5 can be a little bit different, but the isotopic ratio is usually pretty accurate. So in other words, the carbon isotope of C13 is usually pretty indicative of what's in the reservoir, whereas the C1 through C5 may or may not be. Now, certainly you can get systems that can give you a more accurate reading of the C1 through C5, but certainly those are costly. So, okay, so we went through and we collected them and we sent them in for analysis, and each one of these red dots represents a mud gas sample that's taken and sent to the lab. And these are the methane isotopes that were derived from this well. And so these two wells, and so one is we sort of come down the target zone, we're about minus 42 per mil, sort of here. Come across, as we get kind of down here, you actually see the methane increasing for several points, and then as you come back up, you're able to see it come back into what we normally see in the target zone. This target zone that's sort of across here is very consistent when we step through it. It looks like there's some deeper gas that's here that's sort of made into this Marley zone that's a little different from what you had. So this is what we saw while drilling, and one of the important things to keep in mind is, or one of the advantages of taking mud gas while drilling, is that this is before we frack the well. In other words, we haven't fracked it, haven't hit anything. This is just what's in the reservoir that we see while drilling. And so another thing that we sort of look at is the ethane isotopes. So again, which is sort of C2. And if we look at those, they're pretty consistent even as we go through here and come back up and around, and again, throughout the lateral. So I can put the mud gas, but mud gas may drop off as far as the total gas concentration, but you're not really seeing a big change in the ethane ratio, but you're seeing a big change in the methane ratio. So what might that indicate? Well, whenever we look at, so this is a pretty wordy slide, but to sort of show it, so we had this well that's originally making pretty low making pretty good EUR as far as making volume of gas, but not really making the barrels that we'd like. You can see the C1 is isotopically heavier, implying it's a fair amount more thermally mature than this well is very close by, whereas the C2 is pretty similar. So what this implies is that this well 1 is connected, fracked into this deeper zone that you saw whenever you went into the Marley interval. Well, it's producing a material amount of gas, and that's impacting what you're seeing. Since it's very dry gas, it's basically only C1 or methane. So there's not very much C2, so you don't see much isotopic impact because it's not contributing much C2 or C2 through C3, C4, any of the heavier stuff. And so that's kind of one of the indications here. This one, it turns out that interval just isn't a very good producer. The porosity is not quite as good as you like, and so it doesn't meet your pre-drill expectations for how good the reservoir might be because of things like porosity and permeability, but it implies there may be a deeper reservoir that's down there that might have some gas that you might be interested in looking at. Now, of course, there's other factors you look at before you go after that as a target, but it may indicate that there's something there for you to look at. All right? So we'll go to the second example. This is another example of a shale somewhere in the world that exists. And you had three sort of zones that people had drilled. It's an area that had been drilled for a while, and there's a buildup of wells that exist. And so you have some wells that are here that are kind of in the zone that is good in the sense it's making, the GRs are pretty low, which you'd like, and it's making good oil. So in other words, lower GR that you want good volumes of oil that's coming out of them. So these are green. This is kind of what you'd like. These are your good markers. You have another zone of wells that have higher GRs than you might expect, that you might anticipate from their location and some other information that you have. They still have pretty good EURs. They just have a lot more gas than you want to have with them. Then you have a final set of wells. Obviously the big producers, everybody drills a bunch of wells. There's a few wells in the areas, and then the poor producers. So this has a high GOR and a poor EUR, so they don't produce very much, and they don't have such good pressure. And there aren't very many wells that are drilled here. And so, I guess the point to make is if you're going to collect this type of data, for example, you're going to collect mud gas data while drilling, you start to collect it while the well is drilling. If you do that after, you can certainly get wellhead samples after the well is drilled, but if you don't collect it while drilling, it's very hard to go back and get that data. So whenever you drill into a new or step out area, it might be worth considering collecting that type of data. All right. So the first well, it's an area that has low GR, good oil producing wells. So there's a couple of wells that are drilled. So what I've shown here is sort of a non-source reservoir. It's a reservoir interval that's sort of what some people might call a crap rock, where it's got poor, from a conventional standpoint, poor porosity and perm, but it still has, at least presently, but it still has some porosity and perm, certainly above what you might see in some mudstone targets. And then you have sort of a low perm seal zone that's kind of very, very clay rich, but doesn't have a lot of organic richness in it. And you have organic rich intervals that are broken down. This example into 4 A, B, C, D. There's probably, this is to sort of illustrate the point is there's multiple zones that are here. So again, whenever we're collecting these mud gas samples while drilling, whenever we look at the LC13 of the methane and the ethane, it's about -40. We go into the seal zone. We get something that's a little bit isotopically lighter, but not very much. And then whenever we step into the target zone B, you see a pretty big change. Target zone C, that's pretty different from what you have above. If we sort of average out what we have in the lateral here, it's about something like a 44 versus the 40 C2. So there's a pretty sharp contrast between where you have between where you sort your non-source reservoir and your sort of the seal that you invoke, or the seal that you might think exists here. And obviously, I should say this is a positive because it implies that gas is not leaking out of it. The other thing could be interesting or might be worth noting is it's isotopically heavier, and perhaps leaner this gas that's shallower versus this gas that's deeper implies, again, that it may not be a vertical migration. You may have some lateral migration. It's possible for this to be less mature than what's above you, but it's also possible for it to be higher maturity depending on the timing of migration of what happened. And so again, you have a little barrier here that causes, and you're able to see a little bit of an isotopic difference between where you have down here. It's a little bit more mature, not hugely, but a little bit more mature. And so sometimes you'll develop internal barriers. Sometimes they can be carbonates, all types of time zones, and they exist as a barrier. And the important thing is when I'm talking about barriers or lack thereof, seals, this is over geologic time, right? So there still may be some kind of frag barrier or reduction barrier that may exist or not exist, but this is over geologic time. And again, all this is prior to the well being stimulated. Okay. So that's what a good well looks like. Okay. A well that's not so good. Well, again, you have a very similar result in the shallower interval. As you get into the lateral, you see something that looks a little bit strange. And so sort of plotted along, trying to line up each of these points that you see here, lateral, a mud gas sample. And just for relative sake, you're increasing maturity as you're going up this y-axis. And so an observation is as you're drilling, so you land the well, and as you come this way, as you get closer and closer to the toe, you actually are increasing the apparent thermal maturity of the gas, particularly the C1. C2, you're not seeing it very much. And again, when you go back in geosteer and you look at it, it looks pretty close to what it is. In other words, there's no real clear zonal. In other words, didn't steer out of zone. It just kind of gets more mature towards the toe there, which is kind of interesting. And if you drill something from the heel, you'll see the same sort of thing. In other words, as we go through the heel, you see this higher thermal maturity gas, and again, less and less as you go out along the lateral. Implying that there's something physically happening at this, where either the heel or the toe over this zone in the rock. So that's a little bit strange. So what it suggests, or one of the things that I'm trying to illustrate here, is that you may have deeper faults as interval 1, 2, 3, some zone that's deeper, but there's a displacement on. And so this displacement dies out before you get to the target zone D, and certainly before you get to target zone A. So there's no displacement, but there is a damage zone that exists around this fault, this break that exists. And so, again, I've sort of shown it as a displacement in the vertical. There could be a strike slip fault as well that could cause a damage zone, depending on what it is that you really wouldn't see here. And it's possible that's associated with what you might see. But that is, maybe you have a deep-seated fault. You're not seeing displacement. There's a damage zone that's able to connect up, and so you have some higher maturity gas moving up from deeper intervals up along this fault into this damage zone that's sort of moving up into the target zone. And this target zone is actually acting in some ways as a seal for the gas that's below it. So again, if you were to produce that gas, so again, you have a seal here, but you're getting contributions from the higher maturity gas down below you, which is causing your GOR to go up, but it's not really, but you're still getting pretty good EUR. You're still getting oil out of it. It's just a higher GOR than you might expect. Okay. Now, in an example where you have high GOR, low EUR wells, right? So this is a well that you get a higher GOR, but you're not getting much production out of at all. So what might you observe there? Well, again, you have very similar values to what you have in these shallower intervals. Along the lateral, it's high. So in other words, it's elevated relative to some of the other areas. Stable carbon. In other words, it's isotopically heavier and more mature. Particularly if C1, C2 doesn't show very much, and it's very consistent with what you see in the shallow interval that you have. So what you might expect here is that you have, so let's look here. So you may have a damage zone that goes not just into this target zone A, but it goes all the way up into the low perm and to the non-source reservoir. And so it's basically a breached track, a breached seal. And so the gas is able to leak all the way up into this target zone and up into this interval that may be a non-source reservoir, and it goes to the blue sky perhaps. We don't know. And another important point is, sort of glossed over some of these, but one of the things I've glossed over is the idea that the timing of this. it's possible that this leak or migration that occurred when this, before some diagenesis may have taken place in this non-source reservoir, so it may have been better permanent, so it may have been easier to leak out at an earlier time. So therefore, again, so just from, I guess, from a geologic point of view, the evidence you'd have is that you'd have good oil and gas producers, have good skills above and below, everything's self-contained, usually get production. You get a higher GOR if you have a fault or some sort of break or disconnect that allows gas from deeper to get into the reservoir. You're able to connect up to below you. But if you have a situation where you have the top seal or the upper seal being problematic or broken or breached, then things leak out and you get just a totally poor well. And I think that to mention, I'll just mention the slide that I showed here, but if you were looking at, say, the TOC and a lot of other parameters of it, perhaps even the log parameters may look very similar between them because the porosity and pearl may be very similar, all the other things I see. It just comes down to the lack of seal. All right. Let's show another example to illustrate some ideas. This is the third example and sort of the last one that we have here. So the idea that sometimes happens is you have a shale that exists and you're down dip, you have good development, you've got good EURs, but GR is real high, you're not making much oil. And the idea is, can we go up dip? This is perhaps a stronger pull whenever oil is a higher price, so there's a big difference between oil and gas. It is, okay, this is organic rich source rock, we've got some good indications here. Can we go up dip and get a higher value well where you've got a lower GR, more oil cut? Okay. So before we go in there, we'll really do our homework and we'll go with it. We were able to find some cuttings that were from a vertical well that's here, and we were able to find some cuttings from one of the wells that we drilled that kind of went deeper, and did vitrite reflectance as opposed to just doing over one short interval. We did a whole well profile and got a pretty good trend for both of these wells. And so looking at the thermal maturity of the rock, looks like this is going to come out to a thermal maturity of about 1.2, 1.3, something like that. And then this is going to, where we're drilling is about a maturity of about 1.6, 1.7. So yeah, you expect a whole lot of condensate. You expect maybe some more up here for its lower maturity. Okay, well, that looks like it's less mature. There's no real clear kinks or anything that would throw it off. Seems like a good place maybe to drill. So people, again, you ask the reservoir engineer or whoever it is, ask you, well, okay, well, what kind of numbers am I putting here as far as yield? What's it going to translate to? And so somebody looks at the Eagle Ford analog in a certain area and thinks, well, Eagle Ford in that area gives about 100, 150 barrels per million cubic feet. I'm going to estimate that this area, this prospective area, is going to give me something on that order. And I'm not sure what kind of total production I have, but I ought to get something like that yield. And oil is a lot more valuable than gas. I can sacrifice a lot of EUR and still make money if I get enough oil with it. So you go ahead and go that way. So people, in the interim, as you pick up the acreage and you start to get everything ready to drill, people have drilled other wells, your other operators drill wells, and sort of you step up again. This is basically giving you 0 barrels per million. You get something that's 20 to 30, then you get 50 to 60 barrels per million. So people are thinking, wow, so it's 100, 150. Well, maybe that looks pretty good. It's something that you're going to go up there. But whenever you actually drill the well, this well that's here, you only get something like 30 barrels a million. You get lower pressure, lower PFP, lower performance. So that's perhaps an unexpected thing. We went up dip and we had less productivity. Well, then one of the questions that somebody may ask is, well, did we just frack into deeper interval like what we saw previously? Well, a wellhead sample is taken, and you look at the prospect well, and it looks like it's a fair amount less mature than what the original development well was in that area. And it looks like it's pretty close to about that 1.2, 1.3 range, something close to that. And that's seen C1, so it doesn't really look like you've got a lot of deeper gas that's mixed in, or that we've really fracked into a significantly different stratigraphic interval from what we saw again with C1. So, okay. So then you may go around each one of these blue dots representing a point of a wellhead sample. So you maybe take this wellhead samples, sort of see a general trend line, where as we get less thermally mature, as we move this direction, the yield goes up. That makes sense. Then we plot what we got for our prospect area. First well we drilled, and we see, well, at this level of maturity, you'd expect something like 70 barrels a million, maybe more, but you got something that's a whole lot less. So 2 points with this. One, if you do this sort of work and you project out, you'd say, well, that 150 barrels a million, that might have been pretty optimistic based on what you have here. The other, an important assumption that's made whenever you see sort of these types of cross plots, and there's a lot of them where they work really well, is that in the area that you're looking at, the type of organic material is the same. In other words, the only control on the yield is the thermal maturity. So that's assumption. Again, in a lot of areas it's not perfect, but it's a pretty good assumption. This is an example where maybe it's not. So again, we just want to understand, okay, the difference between the thermal maturity, maybe some other factors that we have, but we don't get to invoke, or there's no evidence to invoke some sort of deeper connection, some sort of breach seals, anything like that. Okay. So one of the things we may think about is, okay, well, maybe our development, so I've intentionally been pretty vague as to the type of depositional environment it is, but let's say that we have, your area of study is something that looks like this as far as a basin. Your development area is something like here. As you move towards your prospect area, you're moving up dip. You're moving to more proximal depositional environment. Maybe you're picking up something like deltic facies. Maybe you're picking up something that's not as much fully marine. And so you may be encountering things or getting things that are getting you higher order plants they're contributing. You may also have a poor some that's more oxic, and so the type of organic material is being oxidized and sort of being destroyed. So there are several methods that you might get to understand this difference in area that you have. You may have things like biostratigraphy, core descriptions, things like rock eval, depending on what type of thermal maturity you see, and organic petrology might be useful. But also something that I'll mention here and just mention briefly and kind of going through is elemental analysis. So looking at trace metals might give you some idea about what type of, certainly, redox environment you have in this prospect area versus your development area. It also may be useful to compare. So the idea is that you may have some immature samples from the edge of a basin. And one of the questions is, how well does that translate to areas deeper in your basin, or from higher maturity area, lower maturity area? Or if you're looking at analog, if I'm comparing, let's say, the Haynesville to the Eagle Ford, is that a good analog? So where the things I see there in the Eagle Ford, is that a good analog from it, from the depositional environment perspective? So that's kind of the point here. And so the thing that I'd sort of bring up here is that a lot of times people think about, or sometimes people think about, things like the hydrogen index or the relative amount of hydrogen and carbon. So again, some of those are type 1, type 2, type 3, type 4, and things people talk about structured material being this type 3 that's lower, something that's more of an algal marine is sort of a type 2. And physically what this means is there's more hydrogen per unit of carbon. And so it has a much higher generative potential. In other words, it can generate substantially more volume of oil than with something that's type 3. And in fact, that oil can crack to gas and be substantially higher volumes of hydrocarbons. So sometimes people think, well, I've got a type 3 kerogen. Well, it means they're just going to make gas. That's fine. Not only will you make gas potentially, but you may not make as much gas, even as you might see with some of the type 2 that exists. Now, one of the problems, one of the challenges I'll bring up is that, as you can see here, as you become more thermally mature, everything kind of moves down to the axis, to the zero axis. And so a challenge with using this and sometimes other types of organic analysis is that you can get some idea about the potential if you have an immature sample. But if you have a sample that's fairly mature, something that's 1,1, 1,2, 1,3 batronic reflectance, or something along those lines, a lot of this is already kind of cooked out and moved down to where the origin is. So it actually can be challenging to determine the difference between kerogen types on something that's fairly mature, even when you're using rock eval. It's also not a trivial thing to be able to identify organic naturals as well, because they tend to darken up and it may be hard to distinguish between them as you get more thermally stressed. So an exercise that might be useful would be to look at things like trace metals, things that just sort of pencil down, like things like vanadium, nickel. Whereas if you're going down dip, it implies that it's a more oxidative environment down dip, and the fact that these values are lower in the prospect area would make you a little concerned about the depositional environment. It's also very low molybdenum throughout this whole interval that would suggest that maybe the Eagle Ford is not the best analog for the response of thermal maturity to the depositional environment that you have. And so, again, the types of trace metals, one of the advantages of them is because they don't really change with thermal maturity, and so you can get kind of an apples-to-apples comparison even over a fairly large range of thermal maturities. Whereas a lot of the organic measures, that's not necessarily the case. Right? So I'll just have a few key points as kind of the key things that I wanted to talk on. So the key kind of takeaways is that those elements we have in the petroleum system, and again, some of the processes as well, still exist in unconventional systems. Those things exist in a lot of things we would worry about or be concerned about still need to be concerned about in unconventional. There's sometimes a desire, and a perhaps understandable desire, to paint everything as very low risk, everything is very consistent. The ups and downs that you saw in conventional reservoirs no longer apply to the unconventional world, and that's not really true. It may have a different distribution than what you have with the conventional reservoirs, but those factors are still important. Another point is geochemical analysis. Again, this is we can help give you some insights into things like gas migration, seals, and some of the to predict GOR. Again, you can imagine that if you were to drill, say, a pilot hole, you can collect gas while drilling, and depending on how quickly you get the data back, you can make an estimate for how much yield you'd expect to get, or how much what the GOR you'd expect to get for different intervals before you completed them. And that may help you understand either whether you want to go horizontal or maybe you want to go back to intervals later on that you were interested in. You may also get some insight to seals and whether or not you have some concern about them being breached, and maybe that's a big that might be a big risk factor depending on the type of system that you have. The type of organic material that you have is going to have a material impact on the type of hydrocarbons that can be produced, and along with the volume that gets produced. Right. So an important thing to remember is that all TOC is not the same. Things that are more type 2, things that have a higher hydrogen index, are going to be able to generate much more oil, much more gas than something that's a type 3. Another thing that's important is that conversion. So you may have something that after it's converted, say it's a thermal maturity 1.3, 1.4, two TOCs may be very similar, but the original TOCs might have been different. So it's something that you want to keep in mind when you're doing it. And then the other point that's, I think, important is that you want to be sure that you're able to integrate any kind of geochemical observations that you had or ideas with other disciplines like sedimentology, structural geology, to sort of see, okay, well, this sort of indicates this. Does that make sense from a positional point of view or not? And again, one of the real values, I think, is that a lot of times geochemistry can be integrated with engineering, reservoir engineering, production engineering, to understand kind of important questions, things that might be very important to an engineer that a geologist may not be as concerned with, things like wax production, buildup, other types of things. So that's kind of I guess the close to the 30 minutes that I had agreed to talk about. So I guess we'll open it up for questions, maybe for Amy, and then I'll do my best to answer them.
Did I open that? I should open that. Okay. We have a few questions. All right. Go ahead and please place your questions in the chat. You want to know what lab we use for gas compositional and isotope analysis?
What I'd say is that we currently don't have that in-house as far as the technique we'll outsource, and part of that depends on what the turnaround time is required, and they all have to be quality for who we would do it with. But yeah, we would outsource it to depending on several factors.
Let's see. Any other questions? Okay, well, if there's no other questions, we can go ahead and we've recorded this, so we'll have it available to view.
Oh, there's somebody that says they have a question.
One more question? Okay. What is your question? Anybody else in the meeting have any?
Oh, using solid vision reflectance in place of vitreous reflectance. That's.
So the question is, I would like to know the effect of depth on the quality of. Wait.
Okay.
All right. The first one is, what is your opinion on using solid bitumen reflectance in place of vitrinite reflectance?
Definitely quality. So the idea of using bitumen, there's some. It can be fine if you've got some good calibration that goes with it. I think, especially in situations where you can negate migrated gas, and you have some other things like, for example, you're in a lower enough maturity, we have Tmax that you can get a little bit more handle on, or again, mud gas data or gas data or oil data that would help you tie that bitumen reflectance in. On its own, it has a bigger error bar than what you would have with, say, at least in my opinion, than what you would have with vitreous reflectance. Although that's an error. What I'd say is, I think it can be a useful piece of information. I wouldn't necessarily turn it down, but I would put it with a star or a caveat. Know this is from bitumen reflectance, and try to calibrate it with other data that I had, at least initially. And once you've got a pretty good calibration to maybe some other data, you might have a pretty good confidence in it, because I think there's probably multiple ways to calculate the thermometry from bitumen.
Yeah, we do bitumen and we do vitrinite and bitumen reflectance. Charlie Landis does that. Actually published a paper on solid bitumen reflectance that's available if you search for him. So it's Charles Landis has published that, and he's got a good transform that he uses. I think it's really key that you stick with the same petrographer, the organic petrographer, when you're looking at your samples. Somebody that's experienced and that's been doing it a long time. So Charlie, he does a great job, and he has a good transform on it, really good handle on it. He's been doing it for years on bitumen reflectance. How you improve the quality of the vitrinite reflectance is consistency.
So let's see. Another effective depth on quality. So there's a couple things there. So how do you improve the quality of the reflectance? Like Amy said, using the same person, that helps out. I think a useful thing. Well, there's several points to that. One, it's to understand, using the same person. If you have some other data to help calibrate it and kind of ground truth it in some sense. Things like isotope data or other things to help calibrate it. The other thing to remember is that vitreous reflectance has a pretty decent range associated with it. And again, even when you do a whole well profile, obviously I showed a pretty tight one, but it's not uncommon to get thermal maturity estimate somewhere between 1.2 and 1.4. That's pretty good, but that may have a pretty big impact on the commodity that you get. I mean, vitronite, I guess, maybe it was not originally designed to be as granular as people were trying to make it, and so that's something to think about. There's other techniques that people look at, again, things like Tmax. There's other approaches that people have. Unfortunately, vitronite's the most uniform one. If that makes sense, at least for looking at rocks. And then there was another question that was asked up earlier: is like the effective depth on the quality of unconventional reservoirs? Well, that's okay. So I'll do this. So how does it impact it? Well, trying to think of it. Well, it can very much impact it in a positive way, in the sense that depending on if you've got a good seal, you may have good pressure. A lot of the shales in the U.S. onshore have been they've been buried and they've been uplifted, and so their pressure gradient is pretty high. And so when you drill down into it, you're able to get a pretty big pressure boost. And having high pressure really gains a lot of that really covers over a multitude of sins. So from that sense, that definitely can help you. But the other thing, there's some basins, like I guess in the Delaware Basin, where instead of it just being a straightforward sort of bury and uplift, there's actually sort of a basin inversion. So where you're currently shallower was originally buried perhaps shallow now, maybe perhaps buried deeper, which shallow now is perhaps buried deeper originally. So you sort of have that basin that sort of twists a little bit. In that case, going deeper you might get more pressure, so you get more pressure, but you also have lower thermal maturity. Let's see, and so remind me later. What was another question that somebody asked? Okay.
There's a question about if we use a certain tool on well site for.
Have I ever used it, Mass Spec? No, is the answer to that question. Actually,
you can think of us as almost like consultants on some of this data. If you have it and you don't understand it, that's what we can take in-house and take a look at it and tell you what that data is telling you. So all the stuff that Jonathan showed you is stuff that we can do based on any data that you've acquired, and you need help understanding. Yeah, and so we sort of showed gas in some sense because that was the easiest, but you do similar sorts of things with oil. You also can do, again, I sort of blew past it, but some people have questions about H2S, some people have questions about CO2, some people have questions about water. Some of those same sort of ideas that you talk about transmissibility and being able to compartmentalize things out apply for those types of fluids as well. So as a weird question, is working on an unconventional reservoir which is 9,000 feet deep, and want to know if you encountered this kind of setting before. Vitronite plates of 1 to say 1.15, 1.2. Yeah, I mean there's certainly some in the you definitely have some examples of in the Texas Gulf Coast where you haven't had a whole lot of uplifted erosion, and some areas over towards Louisiana where you can be that deep and have that level of thermal maturity. Actually, you can be that deep and be less mature than that. And there's some areas that are yes, different. So have I seen reservoirs that are that way, under that level of depth, that have that level of maturity? Yeah. I mean, yeah. The short answer is yes. Is that, I guess I'm not sure who asked it, but yeah, if you want some more details about looking at that, I'm happy to discuss it. Any more questions? If you do have any questions, you can feel free to email me. I think you all have my email, amynowak@chemostrat.com, and I will send those questions on to Jonathan or whoever else may be able to answer them. If there's not any more questions, I want to thank you guys all for joining us today, taking some time out of your lunch. We will be posting our next webinar. We'll probably do something in probably February, we're thinking, after the holidays. So I hope everybody has a wonderful holiday. Again, please email us if you have any questions. And we look forward to keeping in touch with you all.
Thank you.
Thank you.
I think if we leave meeting, I think if you leave meeting, it'll shut it down.
Yeah, we'll leave meeting.